Welcome to the next talk in the series of CERIAS seminar for Spring 2017. So today we have our own Scott Carr. Scott recently defended his PhD successfully in computer science department, where he worked with Professor Matthias Payer. And then I guess he is going to join NGC soon after finishing his PhD over here. Scott works on typical, let's say, program analysis, dynamic analysis, static analysis in that field. And today he is going to share some of his recent work that he's going to present next week at Asia CCS. And today he's going to talk more about what he is going to talk over there, but obviously a bit more detail. So Scott, you.
All right, thanks. Yeah, so as Professor Zacate mentioned, I'm Scott Carr. I'm a PhD student here at Purdue, and I recently defended. He mentioned that I work with Matthias Payer. Our group's called the Hex Hive Group, so if you want to Google that to find out any more information about the group, you should be able to find that online. So I'm going to be presenting, this talk is on the main research paper for my thesis that I've been working on for 3 years now. So the first thing I'm going to do is talk to you about the problem that I want to solve in my research and what motivates the problem. Why is it important? And then I'll give you the introduction to my talk and background that will make the rest of the talk more understandable if we have this background information already covered. Then I'll talk about the design and implementation of data confidentiality and integrity, which is the name of the project. And then I'll give some highlights of the evaluation. There's a lot more in the paper. Basically, for each of these bullet points, there's more in the paper that you can look into if you're interested. And then I'll wrap it up in the conclusion. So first, our motivation. So I'm interested in, we call it language-based security, which is looking at why the C and C++ programming languages are insecure and why do they lead to security problems. And in particular, I'm just going to call out one recently found vulnerability. If you follow the security blogs, right, you see that new vulnerabilities are being found all the time. But we'll just talk about this one a little bit. So it's called Heartbleed, and the root cause is a missing bounds check, and it's in the library called OpenSSL, which is a crypto library implemented in C. And it allowed a clever attacker to send a message to the server, and then the server would send back its private encryption key, which could allow the attacker to impersonate the server. And this affects any server that uses OpenSSL, which Apache, Nginx, the commonly used Linux web servers all use OpenSSL. And it could affect potentially up to 66% of websites on the internet, according to some metrics. So it's a really big vulnerability that has a high impact in terms of how widely it could be exploited in the wild. So a lot of security researchers are interested in saying, why didn't we already detect Heartbleed? There's a lot of security work in static analysis and bug finding, these different approaches. But currently, none of those found Heartbleed. In particular, I'm going to talk about CFI, which is control flow integrity. And it basically says that I determine what the control flow of this program should be statically, and then at runtime I see, did my program deviate from this static control flow graph? But the Heartbleed bug does not change the control flow of the program. It just simply leaked sensitive data. So that motivates our work, which is looking at attacks that leak sensitive data or corrupt data on a remote server, for example, similar to the Heartbleed plugin, the exploit I described. And so we need new tools to protect sensitive data, like encryption keys or password lists or authentication tokens. And that's what DataShield and data confidentiality and integrity is targeted at. So the key insight of my work, or the key idea, is that some data are more sensitive than others, and they're worth paying overhead to protect. Because my mechanisms in language-based security usually work by inserting additional security checks into the program to check for example, missing bounds checks for array out of bounds. And each of these new additional checks costs overhead. So we're proposing that you want to protect key data with these additional checks. Examples of approaches along these lines that identify a specific subset of data to protect are stack canaries, which are special values that are on the stack that indicate that if the stack canary value changes, that indicates the attacker overwrote the stack and tried to corrupt the return address. Or a similar Another approach is DEP, which says that any code that's in memory cannot be writable. It can only be executable. So attackers would target the code to overwrite the code in memory with their own code and hijack the program. And the final example I'll give you is CPI, which is basically a specialized CFI. CPI stands for Code Pointer Integrity, and it keeps its own protected copy of all the function pointers and virtual function pointers in the program and stops the attacker from tampering with them. So all these mechanisms identify a subset of sensitive data and protect it. And our key difference is that we're enabling the programmer to choose which data is protected. So the policies I mentioned before all have the data that is going to be protected chosen by the designer of the mechanism, and the programmer cannot change it. And the reason that we do partial protection rather than protecting the entire program, for example, bounds checking every single pointer in the program, is that bounds checking every pointer is very expensive. And at a very, very high level, the way our mechanism works, as I briefly mentioned, is that we take the program source code, we compile it with our compiler, and then the resulting binary has additional security checks that are missing from the original program. So this is going to further frame the problem and how our solutions to that problem are going to be based on these assumptions. So we assume that only low overhead is acceptable. So when we say low overhead, ideally we're getting down to 5 or 10% because so this paper theorizes that if it's down, the overhead is only between 5 and 10%, the end user might not even perceive it. We assume that we have the program source code because, as I mentioned, we're a compiler-based mechanism. We recompile the program. And we assume that the original program contains bugs. So the original program should properly process expected input, but the attacker can potentially create malicious input that causes the program to leak sensitive data or to corrupt sensitive data. So the key concept that we're going to talk about is memory safety. So memory safety means that whenever you read and write through a pointer in a C or a C++ program, you read or write the object to which the pointer was most recently assigned. And I'm going to go into detail about the different ways that this can be violated on the next few slides. I'm going to note that confidentiality means memory safety for reading, and integrity means memory safety for writing. So one way that you can break memory safety is a spatial memory safety violation. So say we have the code snippet over on that side of the slide and then a buffer in memory somewhere. So we loop over the initialized I to 0, and we loop over the elements of the buffer, setting them all to some value. And this is fine as long as the buffer of I is still within the bounds of the array. But when we go past the end of the array, we write whatever memory happens to be there. And this is an out-of-bounds write, and it's a violation of spatial memory safety. So we would like to ideally prevent these out-of-bound writes from happening. Another way that you can violate memory safety is temporally. So in this example, we allocate an array on the heap using malloc, write to one of its elements, and then free the buffer. So now it's gone. But we can still use the pointer to write to the an element of buff that is pointing to now deallocated memory. And now in this way, we're writing to an unintended memory location that doesn't contain the most recently assigned object. So this is another way of violating memory safety. So as I briefly talked about in the beginning, why don't we insert checks before every pointer dereference to see if the pointed to object is the most recently assigned object? And the reason is that's overhead, costly in terms of overhead. So state-of-the-art complete memory safety mechanisms have about 100% overhead or more, depending on the program itself and how often it uses pointers. And the overhead is a function of how many of these new checks we insert into the program. So the way we're going to tackle this problem is we're going to define a new policy that allows for protecting only a subset of sensitive data with lower overhead. And we're going to give several ways of implementing this new policy. And finally, we'll evaluate the security of our implementation by seeing if it can detect publicly found or publicly available exploits. So now I'll describe the design of data confidentiality and integrity. The design is that sensitive pointers can access only the intended sensitive object. So we have memory safety for sensitive pointers. Non-sensitive pointers are isolated from sensitive data, but they can point anywhere except sensitive data. And then explicit data flow between sensitive and non-sensitive variables is forbidden. So the compiler is going to apply this policy to the compiled program that it's given. And at a high level, the way this works is that we divide memory into two regions. One contains sensitive data and one contains non-sensitive data. And in the sensitive region, it contains all the sensitive data as well as metadata about those objects, which allows us to insert our bounds checks and track the size of the objects. In the non-sensitive region, we simply have all the non-sensitive data separated from all the sensitive data. And the way the programmer identifies the sensitive data is by using annotations. And our annotations are type-based. So if you add an annotation as shown at the bottom, this makes the entire object sensitive. So if you annotate a struct, it makes all the struct and all its members sensitive. Sure.
So you're making this perfect segregation between sensitive and non-sensitive, but there can be a situation where indeed at least the sensitive part want to read something from the non-sensitive case.
Yep. So currently there's no support for any information flow between sensitive and non-sensitive. So our assumption is that the code that's dealing with sensitive stuff is going to do its own thing, deal with its sensitive data, and the non-sensitive stuff will be totally separate. In future work, we plan to investigate ways of making this safe. So maybe you could have a sanitizer that allows you to write from sensitive stuff down to non-sensitive stuff. But that would be something that we're going to investigate in the future. So along those same lines, if you annotate a struct, all of its members are now sensitive. So this annotation is recursive. One of the key metrics or the key benefits of our approach is that you don't have to make many annotations because we don't want the programmer to have to do a lot of work and change a lot of their code. So when you annotate a struct, all the members of the struct are sensitive, and then recursively, if the struct itself contains pointers to other structs, those types become sensitive as well. And pointers to a type and the type itself have the same sensitivity. The only case where we don't have this recursive rule is for primitives. So integers, chars, floats, they're not ever explicitly sensitive types. And now I'm going to talk about the implementation of our mechanism, which is, as I mentioned, implemented a compiler. We use the LLVM compiler infrastructure. So the annotations look exactly like this. So say we have a struct foo, and we put the annotation before some instance of foo. Now all foos in the program are going to be sensitive. So let's say we allocate a struct foo on the heap using malloc. The first thing we do is replace the normal malloc call with a call to our region-based allocator, which I showed the diagram before with the sensitive stuff on top. So our allocator ensures that this allocation will be in the correct region. The second thing we do is that we want to be able to bounds check all these objects, right? So we have to record this first address of the object and the last address, and we put that in a metadata table, which I again talked at the beginning, it's above the sensitive, non-sensitive region boundary in the memory overview diagram. So we record the base address as the pointer returned by malloc, and the last address is the pointer times the size of the struct. Then let's say now we dereference the pointer to foo. Now is the time that we want to do the bounds checking. So in this example, we have pointer arrow x. Before we can dereference the pointer to determine if it's safe, we look up the bounds of this pointer using the address of the pointer. And then we check that the pointer is between, of course, the first and last address of the object. Now for a non-sensitive object, so anything that hasn't been of the annotated type, we again replace the malloc, but this time we put in the non-sensitive malloc, which ensures that the object will be allocated below the boundary. And then when we dereference a pointer that's non-sensitive, we have to ensure that doesn't point up into the sensitive region. And one way of implementing that is using a mask, as shown here, where we clear the upper bits so the maximum value of the pointer is below the boundary after it's been masked. And then we allow the pointer dereference to happen. So I mentioned that it's implemented in a compiler. The compiler pass has two different parts. It has a module analysis where it finds all the sensitive types, all the annotations that I mentioned before. And then I mentioned the other piece is the data flow piece. So the data, it does an interprocedural context-sensitive analysis to find all the variables that have data flow with the variables of the annotated types, and it makes them all sensitive. At runtime, there is a library for actually separating the sensitive and non-sensitive variables. It has different allocators for the heap variables. It maps, it separates the stack variables and creates a stack dedicated to this non-sensitive region. And then globals are mapped into their regions by a linker script that will map the non-sensitive globals to the non-sensitive region appropriately. And the same thing for the sensitive globals. So now I'll talk about the evaluation of our mechanism. So this is going to be the highlights of the evaluation from the actual paper. So if you're interested, there's a few more case studies in there that you can check out. So a key question that we want to answer is, does our idea of protecting a subset of the data, do we actually observe lower overhead when we have this condition? So this graph shows two experiments for two micro benchmarks that I wrote that were designed to allow me to control what percent is non-sensitive and what percent is sensitive. So the first one is insertion sort. So it creates two arrays. One is a non-sensitive array and one is a sensitive array, and it puts random data in them and sorts them using insertion sort. And the input to the program is the size of the two arrays. How much sensitive data do I want? The number of elements in the non-sensitive array, the number of elements in the sensitive array. And going on the bottom axis from left to right, that's having a higher percentage of sensitive data. So as we would expect, or as our hypothesis was, that as we increase the amount of sensitive data, we're putting in more and more checks or executing more and more checks, and our overhead is increasing. So for point of comparison, we have softbound and softbound CETS. Those are two mechanisms that give complete memory safety. So softbound is complete space.
Okay, that's interesting. It is on. I don't understand this. One second.
Oh, we have a ton of time left. Yes, we have still we have 20 minutes, 25 minutes. Okay, good.
For some reason, you go ahead and continue. Sorry.
Okay, so did he say something? Okay, so as we can see, I was describing softbound and softbound sets. Their total memory safety. So as we move, their overhead is totally independent of the amount of sensitive data because it treats everything the same. In fact, softbound and softbound sets don't even read the annotations, so they don't have any idea how much data is sensitive according to our annotations.
So question?
Sure.
My question is, what do you mean by, so it's an insertion sort, right? So let's say insertion, I'm sorting an array.
Yeah, right.
And half of the elements are sensitive and half are non-sensitive. But then how can we compare? Because there's a clear separation.
So it's not always half. It's 10% are sensitive, 10% are non-sensitive, up to 90% are sensitive.
But then how are you going to compare them? Because you're not going to take anything from the sensitive area and make it accessible. So let's say you want to compare one element in sensitive and another in non-sensitive.
Yeah, sorry, they're totally separate. So it sorts the sensitive array and then it sorts the non-sensitive array. So it sorts two totally separate arrays. It's basically like, imagine you have a program that deals with sensitive data, does a bunch of stuff, deals with non-sensitive data, does a bunch of stuff, and they're totally separate. But it's still sorting. The amount of elements that it's sorting is the same. It's just how much is sensitive and how much is non-sensitive. But they're two totally different arrays. They can't be, you can't have an array that mixes sensitivity. Does that make sense?
Yeah, okay, because I was just trying to understand the experiment. Because especially in your second example, maybe as I increase, let's say you have 10,000 elements.
Yeah.
in your array, maybe the green line is catching up and making it almost equal to the blue line, something like that. So how big was your data set here?
It's pretty big. I think it's hundreds of thousands or millions.
Okay, so
of
it's already
so,
quite huge.
yeah, so I need to run it for a long time in order to make, account for measurement noise and get good results in terms of being run long enough to measure the time accurately. So it's a really big array. It runs for like, I don't know, a minute or something. The other benchmark is find max, which is just a linear scan of the two arrays. And as you pointed out, the overhead of softbound decreases in this. I attribute that to measurement noise or perhaps some optimization that softbound implemented in their compiler that's kicking in on this benchmark. I don't know the details of the implementation of softbound, so I can really only speak to what I've done. Go ahead.
Sorry, yeah. How come the overhead is below 0?
So there's a couple different sources of speed up in the program. One is that when we do the sensitive regions, we're changing the locality and cache effects. So we actually observed in doing our benchmarks that we would tend to speed up programs by using our partitioning and changing the way the allocator works. For the other benchmarks, we actually use the region-based allocator when we evaluate the baseline. Because we have a run that has no instrumentation, then we have a run with our instrumentation, and we compare them to figure out what our overhead is. We found that the regions were giving us a little bit of an unfair advantage because we were increasing locality and having a lot fewer page faults. So we ran everything in the next, the remaining slides that I'll show you with the region-based allocator, which separated the two regions. It's an interesting question, though. Any other questions at this point? So I think I've talked about that a lot. So then the other question that we'd be interested in knowing is, let's say that our hypothesis that we have a really small amount of sensitive data holds, and we're mostly working on non-sensitive data. But we still have to stop the sensitive pointers from ever pointing into the sensitive region. So we evaluated the spec benchmarks in this configuration. The spec CPU 2006 benchmarks are pretty much the standard in my field for benchmarking performance. However, they're not really security critical programs. They're like, one is a chess simulator, one is a Go board game simulator, one is a pathfinding algorithm. So there isn't necessarily sensitive data, but these are simply measuring used to figure out what the overhead is for a variety of programs. So there are along the bottom of this axis are the individual benchmarks, and then the different colored bars are 3 different ways of enforcing the isolation of non-sensitive stuff from sensitive stuff. So in my example in the beginning, I showed we used a mask to clear the upper bits so that the pointer can't point up into the sensitive region, but there's 2 other ways of enforcing that. The first of the 2 is MPX, which is hardware feature by Intel. It actually introduces 4 new bounds registers and explicit bounds check instructions that you can use to do bounds checking. So the way we use this is we put the bounds of the non-sensitive region in the first bounds register, and then every time before we dereference a non-sensitive pointer, we execute or insert the bounds check instruction. So effectively, it's a bounds check implemented in hardware that we can use for the non-sensitive region. The last one, the yellow one bar, is a feature of the x86-64 instruction set called address override prefix. And what it does is it tells the processor to interpret the memory operands of this instruction as 32-bit values. So you put this magic number for the instruction, and then it will assume that all your pointers are 32 bits. So instructions with this prefix can never reference the sensitive region. And that's the 3rd way we can enforce the isolation. So if you compare the heights of the bars, maybe for now focus on the last one, which is the mean, because there's a lot of benchmarks. We can see that masking is the highest overhead because we're loading this value into a register, doing the and then using the masked pointer. Whereas MPX, we can use the bounds registers for free, essentially. We might actually have lower register pressure because we're not using a register to store the mask itself. And then finally, the yellow bar, which is essentially invisible, is the address override prefix, and it's all in hardware, so it's very, very fast, and it has essentially no overhead. Any negative overhead is essentially measurement noise. So the question that arises from this observation is, why would we use the different options? So one reason would be almost every processor has an AND instruction, but not every processor supports MPX and address override prefix. And the other good thing potentially about MPX is we could have multiple sensitive regions, because we could change the values in the bounds registers and there are 4 of them, so we could eventually have 4 different regions as well. That's not currently implemented, but that's sort of an idea that could be interesting to pursue in the future. Any questions about this? Now the question we want to answer is, how much have we improved security? Have we done something that's actually going to detect vulnerabilities and attacks in the wild? So we found a crypto library called Embed TLS, which is now owned by ARM. It's used in embedded devices to do crypto. And luckily for us, there's CVE found in Embed TLS, which is common vulnerabilities and exposures. So the guy that found it wrote a nice blog post showing how the vulnerability worked, and he also had a proof of concept exploit. So we checked out this version of Embed TLS, compiled it with our protection, our compiler, and then checked if the exploit would still work. But no, in fact, we found that we detected the out of bounds read, and we were able to abort the program rather than leaking the server's contents. So we were able to detect that the attack was taking place in a software that's actually used by people out in production and in the real world. Any questions about that? So now I'm going to wrap up the talk and summarize the key points. In DCI, we have stronger protection for sensitive data and relaxed protection for non-sensitive data. And the reason we have this relaxed protection is it allows us to have lower overhead overall. And that's a key metric for getting people to actually use our mechanism, is that people want really low performance or really high performance in practice. And we have lower overhead than complete memory safety. And we suggest that one of the reasons that complete memory safety is not being adopted is the prohibitive overhead. And our security evaluation with Embed TLS shows that if our technique is used and we compile Embed TLS with our compiler, we're able to detect a real vulnerability that was found in the software. And lastly, the compiler is now open source. You can go to this URL and check out the software, use it yourself, compile your own programs, and I would be glad to answer any questions about it or questions about the talk too.
Questions? Okay, so let me start. So my question is that, did you already talking with some people about or some companies who are interested in using this, or what kind of or if not, then what kind of industry can you focus on for this kind of thing?
Yeah, so the interesting thing about my research area is that there is a little bit of a lag between what is the cutting edge research and what is being done in industry. So I mentioned in the beginning CFI, that CFI doesn't protect Heartbleed, but it can protect against different attacks that target control flow. And it is actually being adopted in industry. The new Microsoft, latest Microsoft compiler has a form of control flow integrity. GCC has a form of control flow integrity, and so does LLVM Clang. So the interesting approach for me that I think would be more adaptable to industry is trying to potentially not rely on annotations. Is one, I think, important direction for future work, because we assume that the programmer knows what's important, but in practice, in industry, you would like to have a tool that works automatically and doesn't require you to go back and say, what are the really important things here? You would just like to have it all work out of the box.
Interesting. So, any other question? Okay, so then maybe just one final thing. You immediately jump on both confidentiality and integrity, but let's see if I want integrity only.
Yes.
Is there already something easily solvable?
Yeah, so the interesting thing about confidentiality and integrity is that writes are more rare in programs than reads. So usually you read a bunch of things, you compute some result, and then you write it back to memory. So there's actually a mode in the compiler that only protects writes, that's confidentiality or integrity only. And it has much lower overhead because the writes are rare. We have to check fewer things than we only check writes. If you want integrity of data, then no, pretty much my approach is the only way if you want partial protection. Softbound does have a mode that's writes only that they call out in their paper too. But I think that integrity is actually a more maybe widely applicable approach to industry and end users because it will be low overhead, as I mentioned. A lot of mechanisms focus on stopping the attacker from corrupting the data rather than stopping the attacker from reading the data, partly because it's lower overhead to protect integrity, but confidentiality on its own obviously doesn't make sense because he can just overwrite, the attacker can just overwrite your protection mechanism to like turn it off. So you need integrity. So mechanisms do focus on integrity. Any other?
Okay. Well, let's then thanks him again. Okay.
Thanks.